We are starting with integration. Today we'll be learning the type 1 problems of integration. The type 1 of integration is categorized as CTS. CTS stands for completing the square type. The CTS is divided in 3 sections. CTS type A, which consists of the problem of the category 1 upon ax square plus bx plus c. CTS type B of the category integral of 1 upon root of ax square plus bx plus c. And CTS C of the category integral of root of ax square plus bx plus c. This type is the basis of all the other remaining types. We'll be picking up one example of each category today. Starting with CTS A.
One second.
Example of CTS A. We'll take up an example of, say, integral of sec square x upon 2 tan square x plus 7 tan x plus 13. Remember, for every CTS category, the first basic rule is that the coefficient of x square should be 1. But here, one more thing, we have an example of method of substitution. So at the first step, we'll take substitute tan x equals t. We'll differentiate. We'll get sec square x dx equal to dt. And our problem will now reduce to integral of dt upon 2t square plus 7t plus 13. Continuing. Now, the first point, as I told you, the coefficient of x square should be made 1. Doing that, we get integral of plus 13 upon 2. Now, completing the square, the reason being we take half of the middle term and add the square of that, and on simplifying we'll get the step as integral of 1 upon t plus 7 upon 4 the whole square plus root of 55 upon 4 the whole square. We'll now apply the formula of integral of 1 upon x square plus a square, and the final answer of this thing would be equal to 1 upon root 55 into 2 tan inverse of 4 tan x plus 7 upon root 55 plus c. We'll now pick up an example of CTS category B. In CTS category B, it is of the category integral of 1 upon root of ax square plus bx plus c dx. We'll pick up a simple example of integral of 1 upon root of 21 plus 4x minus x square dx. Note one thing, whenever you are working with a root and we have a plus and a minus, the x square is with negative. We will always follow the step of writing this as root of 21, and we will take the minus common from these two terms. The answer we'll get is minus of x square minus 4x. Now we'll apply completing the square method. We'll take half of the middle term and add the square of that term and subtract the square of that term. 1 upon root of 21 minus x square minus 4x. Now we are adding plus 4 minus 4 in this bracket. Continuing, integral will now become 1 upon root of 21 minus x minus 4 the whole square, and please note inside the bracket the minus of the minus will become plus 4 again. We have integral of root of 5 square minus x minus 4 the whole square. Applying the formula, our answer would be our answer would be sine inverse of x minus 2 upon 5 plus c. Please note it was x minus 2 the whole square here. Next type, this would be CTS type C of the category root of ax square plus bx plus c. Taking an example, say integral of root of 9x square minus 4 dx. In this case, we can write this as 3x the whole square minus 2 square. Applying the formula of root of x square minus a square, we'll get the answer as x upon 2 into the question minus a square upon 2 log mod x plus this entire part 9x square minus 4. And since there is a coefficient of x as 3, we are going to divide the whole term by 3 plus the constant. The final answer, x upon 2 9x square minus 4 minus 2 upon 3 log mod 3x plus root of 9x square minus 4 plus c. Going for the type 2 problems. The type 2 problems in integration would be mainly considered with a linear and a quadratic term. We'll divide this again into three halves. First one would be integral of the type px plus q upon ax square plus bx plus c. What we call them in general as linear upon quadratic problems. Second, px plus q upon root of ax square plus bx plus c, which will be of the category linear upon root of quadratic. Third, integral of px plus q into root of ax square plus bx plus c, which is of the category linear into the root of quadratic. Again, this type of linear in quadratic, we'll call this as type A, type B and type C. Now let's focus on linear upon quadratic category. In this type, you should always first check whether the denominator is factorizable or not. The denominator, that means the quadratic I'm talking about. If the denominator is factorizable, always we'll be using the partial fraction, which I'll be doing it in my next video. And if the denominator is not factorizable, we'll be following a technique which will be shown later on. Let me pick up an example of denominator being not factorizable and of the category linear upon quadratic. Let's pick up an example. We are under category of linear upon quadratic. Say example is integral of 2x plus 3 upon 2x square plus 3x minus 1 dx. We are integrating a linear term upon a quadratic term. As I told you, we'll first ask ourselves whether the denominator is factorizable or not. In this case, we observe it is not factorizable, and we'll be following one procedure now. And the procedure is simple. We'll always try and write the denominator as, we'll always try and write numerator equal to a times derivative of the denominator plus b. That is, I'm trying to write 2x plus 3 equal to a times derivative of 2x square plus 3x minus 1 plus b. Simplifying, 2x plus 3 equals a times 4x plus 3 plus b. 2x plus 3 equals 4ax plus 3a plus b. Now, I'm comparing the x term with the x term and the constant term with the constant term. On simplifying, we'll say that 2 is equal to 4a and a is equal to half. 3 equals 3a plus b, and therefore simplifying, we'll get the value of b as 3 upon 2 by substituting the value of a as 1 by 2. Once we have obtained these two things, I'm going to write 2x plus 3 equals half of 4x plus 3 plus 3 by 2. Just by mere checking, you can see that this term is always equal to this term. Now, what have we obtained by this? We have just changed the entire format of writing 2x plus 3. Now, this 2x plus 3 will be written as this term. My integral will now convert to half of 4x plus 3 plus 3 by 2 upon 2x square plus 3x minus 1 dx. Splitting both the terms, my integral will be splitted as 4x plus 3 upon 2x square plus 3x minus 1 plus 3 by 2 integral of 1 upon 2x square plus 3x minus 1 dx. Always remember, after doing this step, the first part of the integral will always be of the category f dash of x upon f of x dx. And this part, if you can closely observe, this is our CTS type A, which we did in the previous video. Applying formulas in both the cases following the steps, my final answer of this integral would be half of log mod 2x square plus 3x minus 1 plus 3 upon 2 root 17 log mod 4x plus 3 minus root 17 upon 4x plus 3 plus root 17. So basically, after understanding this problem, our basic criteria of solving linear upon quadratic, always remember, whenever you are solving linear upon quadratic category, that is px plus q upon ax square plus bx plus c, the standard method is as follows. We will try to write the numerator as a times derivative of the denominator plus b. That is, px plus q will be written as a times derivative of ax square plus bx plus c plus b. Next step, from this we will derive a and b, will be our step 2. Once we get a and b, we'll substitute in the sum and we will split in two integrals, in which one category will always be of the category integral of f dash of x upon f of x dx, and the other part will always be CTS type A. To the next type, we will now be solving the category of linear upon root of quadratic. Example, integral of x root of x plus 1 upon x plus 3 dx. Now at the first glance, we don't even see that there is a quadratic here, but what we can do to get that is, we'll be multiplying and dividing by root of x plus 1. So at this step, it is x plus 1 upon x plus 3, and I am now introducing the term of multiplying by x plus 1 upon x plus 1. By doing this, I'll get integral as x plus 1 upon root of x plus 3 into x plus 1 dx. Solving this integral, we get x plus 1 upon root of x square plus 4x plus 3 dx. Now observe, this converts to the category of linear upon root of the quadratic. The steps are almost identical to the previous case. We are going to write the numerator as a times derivative of the denominator plus b. So x plus 1 plus a times derivative of x square plus 4x plus 3 plus b. X plus 1 equals a times 2x plus 4 plus b. X plus 1 equals 2a x plus 4a plus b. Equating the like terms, 1 equals 2a and therefore a equals half. 1 equals 4a plus b, therefore b equals minus 1. After this step, we are going to write the numerator as x plus 1 equals half of 2x plus 4 minus 1. We'll be using this value in our integral. Integral converts to half of 2x plus 4 minus 1 upon root of x square plus 4x plus 3. Now, as done in the previous case, we'll be splitting these two terms. Half of integral of 2x plus 4 upon root of x square plus 4x plus 3 minus integral of 1 upon root of x square plus 4x plus 3 dx. We again get two integrals. This integral is of the category f dash of x upon root of f of x dx. And observe, this is the category of CTS B, which we learned previously. Applying the respective formulas, the last step will convert to root of x square plus 4x plus 3 minus log mod x plus 2 root of plus root of x square plus 4x plus 3 plus c. So whenever we have px plus q upon root of ax square plus bx plus c, our step would be numerator equals a times derivative of denominator plus b. That is, px plus q is equal to a times derivative of the denominator, that is ax square plus bx plus c plus b. Step 1. Step 2, we are going to find a and b. Step 3, separate the two integrals, and always in the first part of the integral it would convert to the category of f dash of x upon root of f of x, and the second category, the second integral, will always convert to CTS type B. Going for the third category of linear into root quadratic. Example, x minus 5 into root of x square minus 1 dx. In this case, again we are going to write x minus 5 as a times derivative of the term, that is the quadratic, plus b. X minus 5 would be a times the derivative of x square minus 1 would be 2x plus b. X minus 5 equals 2ax plus b. Comparing the like terms, x with the x and the constant with the constant, 1 equals 2a, and therefore a equals half. B equals minus 5, and therefore x minus 5 can be written as 1 by 2 into 2x plus b. I'm writing this step in this fashion. Continuing further, our sum will now convert into integral of x minus 5 into root of x square minus 1. Now instead of x minus 5, we will write this as half into 2x minus 5 root of x square minus 1 dx. I'll split the integrals as half integral of 2x root of x square minus 1 dx minus 5 integral of root of x square minus 1 dx. At this step, after separation, check that this is of the category integral of root of t. When I substitute x square minus 1 as t, 2x dx will become dt. And this is of the category CTS-C, which we discussed previously. Applying the formula, the last step would look like 1 upon 3 x square minus 1 raised to 3 by 2 minus 5x upon 2 root of x square minus 1 plus 5 by 2 log mod x plus root of x square minus 1 plus c. So in generality, our steps would be, whenever we have integral of px plus q into root of ax square plus bx plus c, our steps would be the linear term px plus q is a times derivative of that quadratic term plus c. Step 1. Step 2, we'll find a and b. Step 3, separate the two integrals, and always in the first step of the integral, it would be of the category integral of root t dt, which will convert to t raised to 3 by 2 upon 3 by 2, and the other part would always convert to CTS type C. We are now starting with type 3 integrals. Type 3 integrals are solved with the method of partial fractions. In this, the denominator of the problem will look like any one of these four categories. The first one being x minus a into x minus b. There will be two different types of brackets in the denominator. What we call them as non-repetitive linear. Linear. The second one being x minus a the whole square into x minus b. Since this is a squared term, it is repeating itself. We call them as repeated linear. Third category will have linear and some quadratic term along with it. We call this as partial fraction in the category of linear with a quadratic. This is all in the denominator, please note. And the fourth category with x square plus a into x square plus b, there would be two quadratic with the quadratic. Here the method applied to get the answer would be by the method of replacement. We will replace x square by t and then solve the partial fraction. Let us take up an example of non-repetitive linear and understand how do we solve this. Partial fraction type A, partial fraction of the category non-repetitive linear. Let me take up an example. Integral of x square plus 2 upon x minus 1, x plus 2, x plus 3 dx. Remember one rule very clearly in partial fraction. In all the subtypes, the degree of the numerator should be strictly less than the degree of the denominator. Checking the degree, the numerator is of the degree 2 and the denominator, if we open up the bracket, would be of degree 3. So the condition is satisfied. Now this problem of x square plus 2 upon x minus 1, x plus 2 into x plus 3 will be written as a upon x minus 1 plus b upon x plus 2 plus c upon x plus 3. After solving for this partial fraction, we will get the value of a as 1 upon 4, b as minus 2 and c as 11 upon 4. Once we obtain these values, we are going to substitute in the integral, and the integral will convert to 1/4 of integral of 1 upon x minus 1 dx minus 2 integral of 1 upon x plus 2 dx plus 11 upon 4 integral of 1 upon x plus 3. Applying the formula, our final answer would be 1 by 4 log mod x minus 1 minus 2 log mod x plus 2 plus 11 upon 4 log mod x plus 3 plus c. Now we'll go to the next category of partial fraction, type B, of repeated linear. Example, integral of 3x minus 2 upon x plus 1 the whole to the power of 2 upon x plus 3 dx. Please note, it is because of this term of power 2 we are calling this as repeated linear. We'll represent this entire fraction as a upon x plus 3 plus b upon x plus 1 plus c upon x plus 1 the whole square. On simplifying, we'll get 3x minus 2 equals a into x plus 1 the whole square plus b into x plus 1 into x plus 3 plus c into x plus 3. To find the values of a, b and c, we'll first get a. We observe in the a part, we do not have the term of x plus 3. We substitute x equals minus 3 and we get a equals minus 11 upon 4. Next, we'll find the term c, because it is easier to get this as I have x plus 1 and x plus 1 with both the terms of a and b. So we first find c. To find c, we'll substitute x equal to minus 1. By doing this, a and b both would become 0, and we'll obtain the value of c on solving as minus 5 upon 2. Now to find b. To find b, I'll choose any value other than minus 3 and minus 2. I am choosing the value as substituting x as 0. By doing this, I'll get the equation as minus 2 equals A plus 3B plus 3C. And on substituting the values of A and C in this equation, I'll finally reach to the step of getting the value of B as 11 upon 4. Substituting the constants A, B and C in the equation, my integral will be minus 11 upon 4 integral of 1 upon x plus 3 minus 5 upon 2 integral of 1 upon x plus 1 plus 11 upon 4. I think there's an error, sorry. When we substitute A, B and C, the terms would be integral of minus 11 upon 4 1 upon x plus 3 dx. Instead of b, we'll write again plus 11 upon 4 integral of 1 upon x plus 1, and instead of c, we'll write minus 5 upon 2 integral of 1 upon x plus 1 the whole square. Our final answer on integrating this would be 11 upon 4 log mod x plus 1 upon x plus 3 plus 5 upon 2 of 1 upon x plus 1 plus c. We are at partial fractions. We are now going to the third subcategory, linear with quadratic. Example, integral of x upon x minus 1 upon x square plus 1 dx. Again, observe the power of the numerator is less than the power of the denominator. We have a quadratic term, we have a linear term. In this category, we split the term as x upon x minus 1 equals a upon x minus 1, and whichever term is with this quadratic, we are going to write this as bx plus c upon x square plus 1. Now x is equal to a into x square plus 1 plus x minus 1 into bx plus c. Our aim is to now find the values of a, b and c. First we'll get a. To get a, what we do is this term we try to make it 0, and I'll be taking this x minus 1 equal to 0. Taking x minus 1 equal to 0, I get x equal to 1, and we get the answer as 1 is equal to 2a, and the answer of a is half. After this, we'll find the value of c. Remember, to find the value of c, we shall always take the value of x equal to 0. To get c, I am taking x equal to 0. When I take x equal to 0, my answer is 0 is equal to a plus minus 1 into c. And from here, I'll substitute the value of a as 1 upon 2. So 0 equals 1 upon 2 minus c, and therefore c equals half. Now finally we are going to find the value of b. To get b, we are going to take any value of x other than 0 and 1. Say I take a random value as x equal to minus 1. Please note it should be a value other than these two. Substituting, I'll get the equation as minus 1 equals 2a minus twice of minus b plus c. Simplifying this, I'll get the value of b as minus 1 upon 2. Taking the values of a, b and c, the integral will convert to integral of 1 by 2 of 1 upon x minus 1 dx plus integral of bx plus c. So instead of b, I'm going to write minus half x plus half the whole upon x square plus 1 dx. We'll now split these two terms. Half log mod x minus 1 minus half x upon x square plus 1 dx plus 1 by 2 integral of 1 upon x square plus 1 dx. Observe, this is of the category f dash of x upon f of x. Just as the derivative of x square is 2x, we are going to adjust this 2 and a 2 here. Coming to this category, this is our type of CTS category A, which we learned previously. Applying the respective formulas, the final answer would be 1 by 2 log mod x minus 1 minus 1 by 4 log mod x square plus 1 plus tan inverse of x upon 2 plus c. We are now going to the final type of partial fraction of the category x square plus a, x square plus b, and we'll be looking at the method of replace x square by t. Let's take up an example. So we have an integral of x square upon x square plus 2 to x square plus 1 dx. Whenever you observe there are x squares and x squares, and there's a plus in between over here, since we cannot factorize this further, we are just for solving the partial fraction, only for that moment, we are going to replace x square by t. Please note, we are not substituting, we are instead only replacing it temporarily, so that I can write this in the form of t plus 2 into 2t plus 1. Observe carefully, this now converts to non-repetitive linear partial fraction, which I can now write it as a upon t plus 2 plus b upon 2t plus 1. On simplifying this partial fraction, we will get the value of a and b as a will be equal to 2 by 3 and b will turn out to be minus 1 upon 3. And therefore, my integral will be written as 2/3 of integral of 1 upon x square plus 2 minus 1/3 of integral of 1 upon 2x square plus 1 dx, both of the categories CTS type A. Applying the formula, the final answer is root 2 upon 3 tan inverse of x upon root 2 minus 1 upon 3 root 2 tan inverse of root 2x plus c. Now we are going to learn about some very unique substitution which will be helpful in the coming types. The first unique substitutions, would be root x equal to t. Now whenever I substitute root x equal to t and I differentiate at the next step, my answer is 1 upon 2 root x equal to dt by dx. Now I can utilize this substitution in two manners. The first manner is in general, as we always do it, as say writing it as dx upon 2 root x equal to dt. And in the second method, I can say that dx is equal to 2 root x dt. Now if you observe, this root x itself has repeated, and I can say that dx is equal to 2t dt. Now I can use this as my dx, and I can also utilize this as my dx depending upon my situation. The next substitution which shows this behavior is tan x equal to t. When I differentiate tan x equal to t, my derivative is sec square x is equal to dt by dx. This again can be utilized in two ways. The first method is sec square x dx is dt. And in the other method, I will say that dx is equal to dt upon sec square x. Using the fundamentals, I can say that this is dt upon 1 plus tan square x. And if I observe, this tan x was my substitution, so I can say that this is same as dt upon 1 plus t square. So, given in the examination, I can use this and even this as my substitution based on my requirement. The third substitution of this category is log x equal to t. So when I differentiate log x equal to t, my derivative is 1 upon x equal to dt by dx. This can be again utilized as either as dx upon x equal to dt in a normal problem, or in a unique way I can use this as dx is equal to x dt. And using the laws of logarithm, if log x is t, we always know that x can be written as e raised to t. This is the exponential form, and my dx using this value will become e raised to t dt. Fourth such substitution is e raised to x equal to t, which when you differentiate you get e raised to x equal to dt by dx. Can be utilized again in two ways. E raised to x dx is dt, or I can say that dx is equal to dt upon e raised to x, and therefore dx can be used as dt upon t. These are the four different types of substitution where the term which you are substituting is present in some way in that derivative and we utilize it. Going for type 4. Type 4, we'll be learning integral of u into v dx, and also we'll be learning integrating e raised to x f of x plus f dash of x. Now coming to integral of u into v, whenever we want to multiply two functions in integral, we first check the order of Liat, where L denotes the logarithmic term, I denotes the inverse term, A denotes the algebraic term, T denotes the trigonometric term, and E denotes the exponential term. Example of each category. This is of the category say log x. Here the examples of inverse would be sine inverse x, tan inverse x, etc. Algebraic term are like x, x square, x cube. Trigonometric term like sin x, cos x, tan x, etc. Exponential term of the category e raised to x and 2 raised to x. So we keep it in the order of Liad. Coming to an example, let's see an example. Say if I were to integrate cos inverse of root x. At the first step, when I see root x, I'm going to substitute root x equal to t. Now, when I differentiate, I'll get 1 upon 2 root x equal to dt by dx. Now observe, here is a situation where in my derivative I'm getting 1 upon 2 root x, but I cannot see that in the question. So here is where those some unique substitution will come into play. I'll be writing dx as 2 root x dt, and since root x is same as t, I'm going to claim that dx is same as 2t dt. Continuing with my integral, now our integral will look like integral of cos inverse t into 2t dt. 2 is a constant, jumps out. We have the integral of cos inverse t into t dt. Now observe, this is of the category u into v, where this is my inverse term and this is my algebraic term, which satisfies that Liat rule. I'm keeping I the inverse term earlier and algebraic term later. Applying the formula of u into v, we'll get the term as 2 times brackets t square cos inverse of t plus integral of t square upon root of 1 minus t square with a half outside. Taking the 2 inside the bracket, we get the term as t square cos inverse t plus, we'll be adjusting plus 1 minus 1 here, t square minus 1 plus 1 upon root of 1 minus t square dt. Simplifying, my integral will be t square cos inverse t minus integral of root of 1 minus t square plus integral of 1 upon root of 1 minus t square dt. In this part, I'm going to apply the formula of CTS category type C. This is of the category CTS type B. Applying both the formulas, my integral will convert to t square cos inverse t minus t root of 1 minus t square upon 2 plus sine inverse t upon 2 plus c. I'm substituting the value of t as root x. My final answer will become x cos inverse root x minus root x into 1 minus x upon 2 plus sine inverse of root x upon 2 plus c. This sums up our integral. In type 4, we are now continuing with the integral of e raised to x f of x plus f dash of x dx. Let's take an example. Integral of log x upon 1 plus log x the whole square. Substituting log x equal to t. Differentiate 1 upon x is equal to dt by dx. We observe there is no term of 1 upon x in our integral. We'll take the help of our unique substitution and I'm going to write dx is equal to x dt. X will be rewritten as x is equal to e raised to t dt. By the formula of logarithms, if log x is t, we know that x is equal to e raised to t. Rewriting the problem, integral will be equal to integral of t upon 1 plus t the whole square, and instead of dx, I'm going to write e raised to t dt. Now observe, this now converts to the type of integral of e raised to x f of x plus f dash of x. Integral of e raised to t upon 1 plus t the whole square. We'll write this as e raised to t plus 1 minus 1 upon t plus 1 the whole square dt. E raised to t 1 upon t plus 1 minus 1 upon t plus 1 the whole square. This is now e raised to t. This becomes my function of t and this is the derivative of the same. My answer, e raised to t f of t plus c, that is e raised to t upon t plus 1 plus c, and resubstituting the values of t, my answer is x upon log x plus 1 plus c. Starting with the fifth type, what we'll call this type as the sine cosine integrals. As a short form, we'll write this as sine cosine integrals. We'll be dividing this into 4 halves. Sine cosine A, which would be of the category integral of 1 upon a sine x plus b cos x plus c, or the same thing can be written as 1 upon a sine 2x plus b cos 2x plus c. The second type in this would be of the category integral of 1 upon a sine square x plus b cos square x plus c dx. Third type, which will be based on the formulas of sine of a plus minus b and cos of a plus minus b. And in the D section, we'll be learning to integrate a sine x plus b cos x upon c sine x plus d cos x. The same procedure is also applied for integral of a e raised to x plus b upon c e raised to x plus d dx. These would be the four major types of sine cosine integrals. Continuing with sine cosine A. Under sine cosine A, SCI type A of the category 1 upon A sine x plus b cos x plus c, or I would say 1 upon a sine 2x plus b cos 2x plus c. Let me take a simple example. See, I have an integral of 1 upon 3 plus 2 sine 2x plus 4 cos 2x. Observe, this is the constant, this is the a part, and this is the b part. In this, whenever you see a pattern of this kind, we will start with substitute tan x equal to t, which when I differentiate, I get sec square x equal to dt by dx. Again, utilizing that unique substitution, I will say that dx is equal to dt upon 1 plus t square. Also at the same time, I observe I have sine 2x and cos 2x. I need to find a relationship between sine 2x and the tan term. We make use of half angle formulas and the double angle formulas, where sine 2x is 2 tan x upon 1 plus tan square x, which will now be written as 2t upon 1 plus t square. Similarly, cos 2x is 1 minus tan square x upon 1 plus tan square x, which is equal to 1 minus t square upon 1 plus t square. Utilizing the dx, sine 2x and cos 2x, our question will now look like integral of 1 upon 3 plus 2 into, instead of sine 2x, I'm writing 2t upon 1 plus t square plus 4 into 1 minus t square upon 1 plus t square dt. And instead of the dx, I'm writing the dt term here. It is dt upon 1 plus t square. That is, instead of dx, we are writing dt upon 1 plus t square. After taking the LCM and simplifying, we will get the integral as 1 upon 7 plus 4t minus t square, which when you observe goes under the category of CTS type A, which we learned. On applying the formula, our answer will turn to be 1 upon 2 root 11 log mod root 11 plus tan x minus 2 upon root 11 minus tan x plus 2 plus c. So, whenever you have sine cosine integrals type A, if you don't have those double angles, what we simply do is we substitute tan of x upon 2 equal to t, which when you differentiate and use those unique substitution, you will get dx is equal to 2 dt upon 1 plus t square. And now instead of using double angle, we'll use the half angle formula and say that sin x is equal to 2t upon 1 plus t square and cos x is equal to 1 minus t square upon 1 plus t square. And remember, the last step of this entire procedure will always be the CTS type A method to integrate. The example which we learned was of double angle. You substitute tan x equal to t. Using those unique substitution, you reach dx equal to dt upon 1 plus t square. We substituted that, and again remember, at the last step we will always have CTS type A to integrate the final answer. Going with the next type of sine cosine B. In this type, we will have the integral of the category 1 upon a square sine square x plus b square cos square x plus c. or you may only have a sine square x plus b cos square x plus c. The point is you'll have the terms of sine and cos with a quadratic term. What we do here is we will always divide the numerator and denominator by cos square x. Say for example, I have the problem as integral of sine x upon sine 3x dx. In the first step, we'll apply the formula of sine 3 theta, which is 3 sine x minus 4 sine cube x dx. Simplifying, 1 upon 3 minus 4 sine square x. Observe, it now goes to the sine cosine b category. The steps to be followed are divide the numerator and denominator by cos square x. So we have 1 upon cos square x divided by 3 minus 4 sine square x, the whole division by cos square x. This is to be followed always. In the next step, the 1 upon cos square x, which is in the numerator, is written as sec square x, and in the denominator I'll be splitting this cos square x as 3 upon cos square x and 4 upon sine square x upon cos square x, which will convert to 3 sec square x minus 4 tan square x dx. Remember, there should be no term of sec square x in the denominator. So the term of sec square x, which is in the denominator, is written as 1 plus tan square x minus 4 tan square x, which on simplification will give me 3 sec square x upon 3 minus tan square x. And at this step, I'm going to substitute tan x equal to t. When I differentiate, I'll simply get sec square x dx is dt, and my integral will become dt upon 3 minus t square, which converts to the category of CTS type A, which on simplification and applying the formula will give me 1 upon 2 root 3 log mod root 3 plus tan x upon root 3 minus tan x plus c. Now, in generality, the procedure of solving this entire part is given as follows. Whenever you have sine cosine b of the category 1 upon a plus b sine square x or a plus b cos square x or a combination of these terms, the first step is always divide numerator and denominator by cos square x. Write the numerator as sec square x, and the most important point, there should be no term of sec square x in the denominator. If the denominator still contains the term of sec square x, always substitute that as 1 plus tan square x, substitute tan x equal to t, and go to the CTS method to simplify the same. Going for the third type of sine cosine integrals, sine cosine C. This is based on the formulas of sine of a plus minus b and cos of a plus minus b. Let's take an example. Say I have integral of cos of x minus a upon sine of x plus b. Now be very clear in the step. You have to always adjust the form angle in the numerator based on the angle which is present in the denominator. Now in the denominator I see that the angle is x plus b. So we'll be adjusting the term of b in the numerator's angle. So our step would be cos of x plus b minus a and minus b upon sine of x plus b. The thumb rule of this entire type is to adjust the angle in the numerator depending upon the angle present in the denominator. The numerator is now of the type x plus b minus a plus b taken common upon sine of x plus b dx. Observe, this is of the category cos of a minus b. Applying the formula of cos of a minus b, I have cos a cos b plus sine a sine b upon sine of x plus b dx. In the next step, I am splitting the term of sine of x plus b, which when you observe cos upon sine will give me cot of x plus b cos of a plus b dx plus, and when this term will be given to the other part, the sine of x plus b and the sine of x plus b will cancel, and I'll only get sine of a plus b remaining in the other section. Out of this, cos of a plus b is to be treated as a constant. It becomes cos of a plus b integral of cot of x plus b plus sine of a plus b is a constant, comes out, and I'll be integrating 1 dx. My formula, final answer, cos of a plus b into integral of cot, which is log mod sine of x plus b plus x into sine of a plus b plus c. For the next category of sine cosine category D, they are of the category a sin x plus b cos x upon c sin x plus d cos x, or we can also integrate a e raised to x plus b upon c e raised to x plus d with the technique. Let's take an example. Integral of, say, 2 sin x plus 3 cos x upon 3 sin x plus 4 cos x dx. Here we'll be writing the numerator as a times derivative of the denominator as we did in those linear category. Just the new thing would be that instead of b, we will have b into the denominator. This term is a new method or a new type to solve into. How do we do this? Say 2 sin x plus 3 cos x plus equals a times derivative of the denominator, which in this case is, say, 3 sin x plus 4 cos x, plus b times the entire denominator, which is again 3 sin x plus 4 cos x. 2 sin x plus 3 cos x is equal to a brackets. When I take the derivative of 3 sin x plus 4 cos x, my answer is 3 cos x minus 4 sin x plus b, there would be no change in the denominator. This would be 3 sin x plus 4 cos x. Now clubbing the sin x terms and the cos x terms together, 2 sin x plus 3 cos x equals sin x inside the bracket, clubbing the terms, minus 4a plus 3b plus cos x of 3a and 4b. Comparing the sin x term with the sin x term and the cos x term with the cos x term, I'll get the equation as minus 4a plus 3b equals 2 and 3a plus 4b equals 3. On solving this simultaneously, I get a equal to 1 upon 25 and b will be equal to 18 upon 25. Now the sum will be written something like this: integral of, instead of the numerator 2 sin x plus 3 cos x, I'm going to present it in this format. I'm going to write this as 1 upon 25 into 3 cos x minus 4 sin x plus 18 upon 25 and the denominator as it is. So we got the values of a and b, 1 by 25, 18 by 25. Substituting those values of a and b at this step, our integral will be 1 upon 25 the term, 18 upon 25 the same term, upon 3 sin x plus 4 cos x. Now we'll split the two integrals. The first integral would be 1 upon 25 integral of 3 cos x minus 4 sin x upon 3 sin x plus 4 cos x. The other term plus 18 upon 25 of 3 sin x plus 4 cos x upon 3 sin x plus 4 cos x. Observe, this becomes of the category f dash of x upon f of x, and this will cancel off and become 1. The final answer would be 1 upon 25 log mod 3 sin x plus 4 cos x plus 18x upon 25 plus c. One more sum of this category is when you have to solve 3 e raised to x minus 4 upon 4 e raised to x plus 5 dx. The entire procedure remains the same. I'm going to write the numerator as a times derivative of the denominator plus b times the denominator. So 3 e raised to x minus 4 is a times derivative of the denominator, that is 4 e raised to x plus 5, plus b times the denominator itself, 4 e raised to x plus 5. My answer is 3 e raised to x minus 5. Taking the derivative, I get this as a 4 e raised to x plus b 4 e raised to x plus 5. Taking the like terms of e raised to x together, 3 e raised to x minus 4 is e raised to x of 4a plus 4b, and we have 5b separate. Taking the like terms of this e raised to x with e raised to x and the constant with the constant, what we get is 4a plus 4b equals 3, and b 5b is equal to minus 4, and b is equal to minus 4 by 5. Substituting this value here, I get the value of a as 31 upon 20. We will now be writing 3 e raised to x minus 4 as this step will now be written as 3 e raised to x is equal to 31 upon 20 of 4 e raised to x minus 4 upon 5 of 4 e raised to x plus 5. In my integral, this will become 31 by 20, 4 e raised to x minus 4 by 5, 4 e raised to x plus 5, the whole division by 4 e raised to x plus 5 dx. Splitting the terms, 31 upon 20, integral of 4 e raised to x upon 4 e raised to x plus 25 dx, minus 4 upon 5, integral of 4 e raised to x plus 5 upon 4 e raised to x plus 5. If you observe, this converts to the category of f dash of x upon f of x, and this will cancel off and become 1. Final answer, integral will become 31 upon 20 log mod 4 e raised to x plus 5 minus 4x upon 5 plus c. Whenever we have a sum of the category sine cosine d, we always write numerator equals a times the denominator plus b times derivative of denominator. We obtain values of a and b, we separate them, and once we integrate, the answer will always look like ax plus b log mod the denominator plus c, or for a e raised to x plus b, it will become ax plus b log mod the denominator plus k.